Today I will be discussing the NeuralODE that I wrote to predict the in-flight trajectory of BYU rocketry competition rockets. As a little bit of motivation for this project, in BYU rocketry on our competition rockets, we run many simulations beforehand to reach a desired altitude or apogee. This is how we receive points in our competitions. However, many of these simulations don't give a full picture of what actually happens come launch day. For example, in this bottom left plot that you can see on this slide, this was our altitude for our previous test launch. We were aiming for 30,000 feet, but we only reached about 23,000 feet. The goal of this NeuralODE is to be able to predict after the first few seconds of flight what that final apogee will be. Therefore, we could implement some sort of air brake or ballast system to correct for an either undershooting of our target apogee or overshooting of our target apogee. To implement this NeuralODE, there are three main steps. The first was gathering and preparing flight data. This included normalization of the data and windowing of the data, since I was dealing with lots of different rocket trajectories that launched for different periods of time. Next after that was creating a latent dimension encoder. I'll discuss that in a future slide. And then finally, creating the NeuralODE with latent space and training and testing that. The first thing to understand about the architecture of this NeuralODE is the latent dimension encoder. So the flight computers that we have on our rockets record lots of information. The two primary pieces of information that are recorded during flight are the altitude and the vertical velocity. However, there are many things that are not collected and recorded that aren't taken into account if we were to pass these two data points directly into a NeuralODE. Things such as drag, thrust, and many other things. Therefore, we need a latent encoder. We need to be able to take our position and our velocity and translate it into a higher dimensional state that will provide a bit more information to our NeuralODE in about its initial flight path. And the way I'm doing that is I just used a standard multi-layer perceptron to generate that latent space. Okay, now to talk about the NeuralODE itself. So the very first thing that we do is we take that initial latent space, that Z naught up there in the left-hand corner, and we also take our initial position and our initial velocity, and we feed that into our NeuralODE. The NeuralODE is a fairly standard NeuralODE. It takes those inputs and uses those to predict a velocity, acceleration, and derivative of our latent space. As you can see, this has the subscript t plus w. So what this is saying is that we're predicting our next time step plus our window. I'll talk about windowing in a second here. But essentially, we're just going to the next step in the rocket's flight, predicting its velocity, acceleration, and derivative of its latent space. And then we're passing this into an ODE solver, which will then return our next position, velocity, and latent space. This is then fed back into the NeuralODE in a positive feedback loop to be able to predict the entire trajectory of the rocket bit by bit, recursively. Okay, now to discuss the specifics of the model architectures. So we'll start with the encoder. It's a pretty small multi-layer perceptron. It has no hidden layers. It needs to be on an embedded system, so it needs to run quick and be responsive to the rocket's flight. So it just has an input, an activation layer, which is an ALU activation, and then an output. And then you pass in the first 10 time steps that are recorded by the flight computer as context for the model so that it can generate that latent space for you. Those can be adjusted accordingly depending on the flight computer and the motor that's on the rocket to account for rocket burnout, as you would ideally want to collect data throughout rocket burnout and a little bit past that burnout so that you can get a full detail of the thrust of the rocket. Now to discuss the NeuralODE itself. It uses quite a few hidden layers with a lot of depth. You can see those layers right there. And between each of those hidden layers, it uses an ALU activation as well. And then for the actual ODE solver itself, it uses a Runge-Kutta 4.5 adaptive solver. Okay, now to get into loss and training. Training this model was a bit tricky. I think that I was lacking sufficient data for this. I had data from 25 flights that were varying in length and apogee. And when I was training these, I used a varying window size. So to explain that a little bit, I started with a window size of 1. So it would look at that first time step and then predict 1 time step forward. And would do that for a few epochs, and then it would switch to a window size of 5. So it would look at that time step, try to predict the next 5 time steps, and then use a loop for that. And I slowly increased that over time. However, as I did that, I found that my losses were flatlining around 100 epochs, which is definitely concerning for a NeuralODE, and definitely something that I have to look into and improve further as I continue to pursue this project. My guess is that I simply need more data for very specific apogees that I train on. Okay, and now for the results of the model. The results were definitely interesting. I found that the window size that I used to evaluate my model largely affected the predicted flight path. So as you can see, if I used a window size of 1, as a reminder, that is taking the current time step and just using that to predict our next time step with our states. So it's very slow, really not ideal for in-flight, but it was pretty spot on for predicting its target apogee and its flight path. However, if we increase that to 4 window size, which means we're predicting the next 4 steps, giving 1 time step, a bit more useful for rocket flight, we got a lot of noise in our path. The apogee was still pretty spot on, but there was a lot of noise along the way. And then if we go to a window size of 10, that just gets even worse. And as you go up in window size, that noise gets worse and worse. I'm currently investigating what the cause of this is. I suspect it's just the lack of data, and perhaps it is an error in how I'm implementing my window size function. Okay, now for further research on how I can improve this model and truly implement it into a rocket for flight. The first is to collect more data. Again, I only had 25 rocket trajectories. If I had more, around 100-ish, I'd imagine that my trajectories would be a lot more accurate and it would reduce a lot of the noise in the data. I also am considering investigating a residual neural network that'll retain information on the drag and other features of the rocket that I'm currently recording in my latent space. I feel that a residual neural network will allow my network to understand that a little bit better. And I'm also going to look into allowing for larger windows to have greater accuracy. The goal is to use a fairly large window size so that in flight, when this is on an embedded system, a rocket can predict its target apogee in several milliseconds to be able to implement a ballast system or air brakes to allow for the target apogee to be reached. And yeah, that's the model that I implemented. Thank you for listening.